Welcome to the deep dive. We're looking at a stack of sources today that really get into something. Well, it's beneath our feet, but it connects so many big things: energy, the environment, history, even ethics.
We're talking about radioactive waste, specifically uranium waste.
Yeah, exactly. And we've got research, articles, notes. It's quite a mix.
It is. And our goal here really is to unpack the most important stuff, maybe some surprising nuggets from all this material. We want you to understand not just what this waste is, but why it's such a persistent issue, a problem that lasts, well, way longer than any of us.
And right off the bat, these sources throw up a real head scratcher, a paradox. We're dealing with stuff that's dangerous for literally tens of thousands of years.
An almost unimaginable time frame.
Right, but then here's the shocker from the data. In 2023, get this, 95% of the uranium the U.S. bought for its reactors came from other countries.
95%, it's staggering.
Think about it. We import almost all the fuel, and then we're left with this legacy that, frankly, we're still figuring out how to handle for millennia.
And to add another layer, some of these sources actually suggest that maybe this waste, this spent fuel, maybe it's not just waste.
What do you mean?
Well, some argue it could be a resource. Fuel for advanced reactors, maybe powering future tech like AI or crypto. So it's complicated. How we even see this stuff is debated.
Okay, let's back up. What is this stuff fundamentally? Where does uranium waste begin?
It starts with getting uranium out of the earth. Mining, basically. Could be open pit mines, underground mines, or chemical methods like heap leaching, dissolving it out of the ore.
Or washing it out.
Sort of, yeah. But no matter how you do it, processing that ore leaves stuff behind. Solid stuff called tailings and liquid stuff called raffinates.
And these aren't just minor bits.
Oh no, they're intrinsic byproducts. And here's the key. They contain most, maybe 80 to 90% of the original radioactivity that was in the ground.
Wow. So the waste has most of the radioactivity.
From the original ore, yes. It's usually stored in these big ponds, impoundments. And if they're not managed perfectly, well, you risk contaminating water or radioactive dust blowing around. Big problems.
Okay, so that's from getting it out. Then we use the uranium, and that creates different kinds of waste, right? The sources talk about levels or classes.
Exactly. It helps to break it down. You've got low-level waste, LLW. Think contaminated gear gloves, tools, filters. This is actually the bulk of it by volume, like 90%.
90% volume.
Yeah, but only about 1% of the total radioactivity. And some of the least radioactive stuff, Class A, might only be hazardous for, say, less than 100 years, which in nuclear terms is kind of quick.
A blink of an eye, relatively speaking. Where does it go?
Usually near surface disposal facilities. Buried, but not super deep.
Okay. What's next up?
Intermediate level waste, ILW. This is more radioactive, needs shielding. Think resins from water purification, sludges, bits from taking old plants apart. Much less volume, maybe 7%, and around 4% of the radioactivity.
Still manageable, maybe, compared to the next one.
Compared to high-level waste, yes. HLW is the really potent stuff. Mostly spent fuel rods from reactors.
The fuel after it's been used.
Right. It's incredibly radioactive, generates a lot of heat, needs cooling, heavy shielding. It's tiny by volume, only 3%.
Only 3%.
But it holds 95% of the total radioactivity. 95%. And this is the stuff that stays hazardous for tens of thousands of years.
That number.
Yeah.
It's just hard to comprehend. Tens of thousands of years.
It really is. And there's also a category called greater than Class C, GTCC. Basically, too radioactive for near surface, so it's generally headed for the same kind of deep geologic repository planned for HLW.
So the big takeaway is volume versus longevity, right?
Okay.
LLW is bulky but shorter lived hazard. HLW is tiny but lasts practically forever.
That's the critical distinction, yes. One's a challenge for decades or centuries, the other for civilizations.
Okay, so we've got this range of waste. How on earth does the U.S. manage it all? The sources mentioned a bureaucratic ballet.
That's one way to put it. It's complex. You've got multiple agencies. The EPA, the Environmental Protection Agency, sets the overall environmental standards. They make the big rules.
And the NRC, the Nuclear Regulatory Commission.
They're the ones doing the licensing and checking for compliance. They enforce the EPA's standards, basically. They oversee the plants, the waste facilities. They're kind of the day-to-day regulators. Some states also have agreements to regulate certain things themselves.
Okay, EPA sets rules, NRC enforces. And moving this stuff, it has to be transported.
That falls under the Department of Transportation, the DOT, working closely with the NRC. You can imagine shipping radioactive materials needs some pretty strict rules.
I bet. And this whole system is built on laws, right?
Yeah, foundational laws like the Atomic Energy Act from way back in 46, the Nuclear Waste Policy Act of 82, and UMTRCA, the Uranium Mill Tailings Radiation Control Act of 78.
UMTRCA. Wasn't that the one that stopped people using tailings for, like, building foundations?
That's the one. Seems obvious now, but yeah, they had to pass a law to stop using radioactive waste rock in construction.
Wow. Okay, so lots of rules. But the sources also point out something strange. The U.S. nuclear fuel infrastructure is called severely atrophied.
It is, and that's partly down to policy history. For a long time, from the late 70s to the mid-2000s, commercial reprocessing of spent fuel wasn't allowed. That pushed reliance onto foreign sources for fuel services.
Which brings us back to that shocking number. 95% of uranium bought by U.S. utilities in 2023 was foreign. Canada, Kazakhstan, Australia, even Russia and Uzbekistan.
Yeah.
Only 5% domestic.
It really flags a major energy independence question, a supply chain vulnerability. It's stark.
And it feeds into this Catch 22 the sources mentioned.
Yeah, exactly. You need high regulation for safety, absolutely. But intense public opposition can drive regulations even tighter, leading to massive delays, huge cost overruns for nuclear projects.
Which, ironically, might make it harder for nuclear to be a timely solution for something like climate change, even if people want it for that.
It's a real tension. Safety is paramount, but the process can become incredibly slow and expensive.
Beyond the paperwork and supply chains, what about the actual environmental damage? The sources talk about scars on the land.
They do. Mining and milling, especially historically, left behind significant contamination. Water pollution is a big one. Arsenic, lead, uranium itself leaching into groundwater or surface water.
And radioactive dust.
Yep, from the big piles of waste rock and tailings. Wind can carry that dust over long distances, affecting air quality.
And those storage ponds, the impoundments?
Often just open-air ponds, maybe a fence around them. The sources describe them as potential toxic cocktail bars for wildlife. Birds land, animals drink, they get exposed to radiation and heavy metals.
There's also radon gas.
Yes. Uranium decays into radium, which decays into radon, a radioactive gas. Outdoors, it usually disperses, but in underground mines, especially poorly ventilated ones, radon can build up. It's a major lung cancer risk for miners.
And radon is actually a common source of radiation exposure for everyone.
It's the largest single source of naturally occurring radiation exposure for most people, yeah. Mostly seeping into homes from the ground.
The sources make it clear this isn't just history, though. There's a legacy of harm, especially for certain communities.
A really crucial point. Look at the Navajo Nation. Decades after the mid-century uranium boom, over half the small abandoned mines and waste sites on their lands are still there, unremediated.
Still causing problems.
Absolutely. Wind blows dust, water gets contaminated. And this has directly contributed to higher rates of cancer, respiratory diseases. It's a terrible environmental justice issue, mirroring how industrial pollution has historically burdened marginalized communities.
And it's not just abandoned sites. The sources mention active facilities too, like the White Mesa Mill in Utah.
Right. An active mill is cited dozens of times by state regulators since 1999 for violations. Testing nearby shows high levels of uranium, nitrates, other contaminants in groundwater. One well near the site had uranium over 6 times the federal drinking water limit. It shows the challenge is ongoing.
So the uranium gets into the water. Does it move up the food chain?
Researchers have looked at that. In streams affected by mining, uranium does accumulate in organisms like insects, caddisflies, and the amount they absorb seems directly related to how much is in the water or sediment.
Does it concentrate more in predators that eat those insects?
Here's where it gets interesting and maybe a bit unexpected. The study cited suggests uranium does not strongly biomagnify.
Meaning it doesn't build up to higher and higher concentrations as you go up the food web?
Yeah.
Like mercury or DDT famously do?
Exactly. It accumulates, it's toxic, but it doesn't seem to follow that classic biomagnification pattern, a scientific nuance there.
Okay, shifting gears a bit. When people think nuclear risk, they often think of big accidents. Chernobyl, Fukushima.
Understandably. Chernobyl in '86. Flawed Soviet reactor design, poor operator training, massive steam explosion, fire, huge release of radioactivity across Europe. Immediate deaths were relatively few, plant workers mostly, but the long-term health effects, especially thyroid cancers from the radiation, are still debated.
And Fukushima in 2011.
Triggered by that massive earthquake and tsunami, led to core damage, hydrogen explosions, significant radioactive releases, huge evacuations. The cleanup cost is astronomical, hundreds of billions potentially. Some critics, like Greenpeace and one source, point to the accident rate and suggest major meltdowns might happen roughly once a decade globally.
Scary thought. But the sources also mention a less famous, but still chilling, incident. Palomares.
Yeah, 1966, off the coast of Spain, a U.S. B-52 bomber carrying H-bombs collided with its refueling tanker midair.
Oh, wow.
The tanker exploded, the B-52 broke apart. Crucially, the conventional explosives in 2 of the H-bombs detonated when they hit the ground. Not a nuclear explosion, but it scattered radioactive plutonium over about 2 square kilometers of Spanish farmland. A 4th bomb fell into the Mediterranean and wasn't found for months.
So nuclear risks aren't just about power plants. Military, transport.
Exactly. It broadens the picture. And these accidents, while dramatic, lead back to maybe a more fundamental point captured in that quote from A. Stanley Thompson.
The one about the most intolerable reactor.
Right. He said, the most intolerable reactor of all may be one which comes successfully to the end of its planned life, having produced mountains of radioactive waste for which there is no disposal safe from earthquake damage or sabotage.
So even if everything goes right during operation, the waste itself is the enduring, perhaps intolerable challenge.
That's the perspective. The long-term management of the waste, the lack of a final agreed-upon solution, that's the core problem for many critics.
Which sets up the big debate today, the nuclear showdown, as one source calls it. Pro versus anti.
It's definitely polarized. On the pro-nuclear side, the atomic optimists, you hear strong arguments for it being essential for climate change.
Reliable, low-carbon power. Operates constantly.
Exactly. People like Bill Gates call it the cleanest, safest, reliable option. Francis Macron talks about jobs, energy independence, low carbon. And the stats are impressive. Over half of U.S. clean energy runs over 92% of the time. It's incredibly energy dense.
And the argument is basically, we need it for net zero.
That's the line from proponents like the IAEA director, Grossi. Reaching net zero requires more nuclear. It's the scientific consensus. They frame it as indispensable.
Okay, but the atomic skeptics have a very different take.
They do. They argue it's too expensive, too slow, and inherently dangerous. And that clean energy claim, they say the whole fuel cycle, from mining onwards, creates pollution. Irene Koch is quoted calling it a cynical gambit, not a real climate solution.
What are their main points?
Number 1 is the waste. Still no permanent solution for the high-level stuff. Over 90,000 metric tons just sitting at reactor sites in the U.S., an unsolved legacy.
And cost and time.
Huge issue. New plants cost billions, take a decade plus to build, often run way over budget and schedule. Renewables like solar and wind are now often cheaper and can be built much, much faster.
What else?
Water use. Traditional reactors need lots of cooling water, a problem in dry areas. And if cooling fails, meltdown risk. And finally, proliferation. Spreading nuclear tech, especially reprocessing, which separates plutonium, increases the risk of weapons development or terrorism.
So the counter-argument, like from Greenpeace, is basically, it's too slow, too expensive, renewables are better, faster, cheaper. It's a dangerous distraction.
That's the core of the skeptical view, yes. The practical hurdles might outweigh any potential benefits, especially compared to renewables.
Looking ahead then, what's being done? Are we getting better at cleaning up the mess?
There's definitely progress on remediation. Scientists are developing better ways to remove uranium and other contaminants from water and soil, using special materials, biological methods. Some new adsorbent materials show really high performance, like atomic-scale MOPS.
So we're getting better at the cleanup. What about that idea of using the waste, reprocessing?
It's a major focus of innovation. The idea is appealing. Take spent fuel, extract the usable uranium and plutonium, reduce the waste volume, and maybe use the extracted materials in new advanced reactors. Companies like Oklo and Curio are working on reactors designed to run on this stuff.
Sounds like a win-win. Less waste, more energy.
On the surface, maybe. But here's the big catch, the security risk we touched on.
The plutonium.
Exactly. Reprocessing separates plutonium. And as Ross Mathkin-Bridger is quoted, getting the fissile material is the hardest part of making a bomb. Once you have separated plutonium, it's much easier.
So widespread reprocessing could make nuclear proliferation or terrorism easier.
That's the huge concern. It creates this direct link between civilian power and weapons-usable material. It's a serious ethical trade-off. Solve an environmental problem, potentially create a massive security one.
Which leads to maybe the weirdest but most profound challenge mentioned. warning the future, like way, way into the future.
Yeah, the 10,000-year problem. If you bury this waste deep underground, how do you make sure people 10,000, 20,000 years from now don't accidentally dig it up?
How do you even communicate across that kind of time? Languages change, civilizations collapse.
Exactly. It spurred some wild ideas. Creating an atomic priesthood to pass down warnings through rituals, building hostile-looking landscapes, fields of spikes, massive earthworks designed to scream, "Danger, keep out," non-verbally.
And wasn't there something about a song?
Chuckles slightly. Yeah, the 10,000-year earworm idea. Create a song, maybe called "Don't Change Color, Kitty," or something equally bizarre and annoying, hoping it's catchy enough to be passed down orally for millennia as a folk warning.
Wow, that's something else.
It sounds almost absurd, but it highlights the depth of the ethical challenge. How do we take responsibility for something that outlasts? Well, possibly everything we know. Philosophers like Michael Peterson use this exact problem to argue we need a whole new way of thinking about our obligations to distant future generations.
So, quite the journey. From discovering that 95% of our nuclear fuel is imported, through the regulatory maze, the environmental scars, the heated debate, and now, these almost science fiction level ethical questions about deep time.
It really drives home that this isn't just about engineering or geology, it's about us. It's about the choices you make, the energy we all demand, and what kind of legacy we leave behind.
So the final takeaway. It seems the nuclear waste problem is more than just waste. It's a profound test of our ability to think long-term, beyond our own lifetimes, for people we'll never know.
Maybe the ultimate atomic punchline, if you want to call it that, isn't just the waste itself. It's how we, as a species, grapple with the consequences of our own cleverness, knowing some things we create might outlast us all, silently warning or maybe endangering the future. Will they thank us or curse that glow in the dark?